To be a short video that talks about how to use NumPy. So let me be blunt. If you already feel comfortable in NumPy, don't watch this video. And if you feel like, okay, I pretty much understand NumPy, but it's been a while since I've used it. Do you know what's the right thing to do? Go to our demo notebook repo on GitHub and look here at Lecture 04 pre-NumPy. You should play with this notebook and turn off this video. But if you're just really feeling uncertain about using NumPy on your own, or you've never used it, hey, watch this video and then go play with the notebook, okay? So what is NumPy? NumPy is really how you do linear algebra in Python. And as we know, machine learning is really all linear algebra. So NumPy is, like if you've ever used MATLAB, NumPy is Python's version of MATLAB. It is made for doing linear algebra. So it's super optimized, really fast, and it's something which is a tool used by many other packages. So scikit-learn is what we're going to use largely in this class, but pandas and stats models and other things you used in Cogs 108 also built on top of NumPy. Even if you're like, oh, I'm just going to go get into deep learning and I'm not going to use this kind of stuff. Well, let me tell you what, Captain Convolutional Neural Network, you are possibly going to be using things like JAX, which is a high performance for, automatic differentiation library that's really built on top of NumPy. So yeah, it could be worth your while if this is not enough tutorial for you to go back and look at these things. But the basic element of NumPy is the array. So when you import NumPy as NP, which because we're lazy programmers, you get a class called NumPy array that you can just construct with lists. And essentially you have to assume that a NumPy array, by default when it's one-dimensional, it should be looked to you like a columnar variable in your head, okay? And NumPy arrays, I thought I cleared all this stuff, so let me just so that I can run it, yeah? NumPy arrays are indexed exactly the same thing as lists are in Python. So the first element of an array, helps if I do this first, right? So the first element of an array is the quote-unquote second element because we're zero indexed. So the data came in as 1, 2, 3, and this is the first element because we zero index. You can slice, so this takes you up to, but not including the second element of the array, right? So up to, but not including the second element. You can start with the first element and go through all the rest of the array. You can even use negative indexing. Negative indexing says that you would start from the back of the array and go back 2 steps. So the back of the array, go back 1, 2, and then go forward. Okay, you can also take strides. So the first, just like lists, the first element is the start of the array. The second element is the end of the array. And the optional third element is going to be the steps. So this steps by 2 instead of by 1. So instead of going 1, 2, 3, the way that it would happen if you did this, we can step by 2 and go from 1 to 3 directly. Okay, so you can use stepping to reverse the order of an array. If you would like a little exercise, please get this notebook live and do that yourself. So NumPy is super useful. Just to convince you, if you would like, you can run these things right here if you've got this notebook live, and you can see for yourself that NumPy with a large array is more than 60 times faster than using a list for the same deal. So it's highly optimized stuff. Okay, multi-dimensional arrays. Multi-dimensional arrays can be specified like this. Every set of brackets, of square brackets, is a dimension. So if we start off with this as an array, this is a 2D array. It's got 2 rows and 4 columns, right? So there's a 2D array, and think of it as a z-stack, as a third dimension of 3 of those 2D arrays. So if you look at the number of dimensions, it's got 3 dimensions. The total number of elements in it is 24, and the shape is a z-stack of 3 and 2 rows and 4 columns. Okay, so you can index multidimensional arrays just the same way that we were indexing previously. So the 0th element tells you you're going to be in this chunk. The first element says you're going to be in the first row. And the second element is 0, 1, 2 on the columns. So that's the number 6. Okay. Yeah, so you can take entire rows or columns or the third dimension, whatever you want to call that, right? So you can do all these things, take little chunks, run this, convince yourself, because it's no good if I try to show this, it's just too slow. You need to work with this if you are confused at this point. So let's see, what else do we want to show? You can reshape arrays. So you can start off with an array that's just a single 0 through 5, and you can reshape it to be a 3x2 array where it goes column major, first 0, 1, we turn 0, 1 in 2, 3 into 2 separate rows. First the first row, then the second row. Okay? Everything in NumPy is row major. Rows happen first. So you can reshape something to be just a 24 long array. You can also flatten, and flatten is equivalent, right? It's getting rid of all the dimensions, and it's going to do it in a row major way. You can create empty arrays of 0s or 1s. You can make arrays not just, single dimensional, but you can make multi-dimensional arrays by passing them in the shape of the array that you want. Okay? You can even copy arrays and just make an array of 1s the same shape as some other array. Okay, it's pretty cool because you can do some basic calculations in NumPy arrays. They have mins and max and other things available to you. And by default, it operates across an entire array. So here I just took a multi-dimensional array, and the min and the max that I got is across the entire array. Okay? You can also do it only along a particular axis. So along the 0th axis, right? So as we go across these elements, These are the minimum values of all of those elements, okay? You can do it across the first axis, and that's going to be across the rows, right? Sorry, it's going to be across the columns. Good job, Jason. So this is this column, this set of columns. Okay. So linear algebra, right? I promised you linear algebra. There's always more than one way to skin a cat. Sorry, cats who are currently on my lap, but that's just an expression in English. So how does that work? Well, vector addition and subtraction looks exactly like regular stuff. You have two different ways to do multiplication with matrices and vectors. You can do Hadamard multiplication, which is just element-wise. So the 0th element of vector 1 multiplied by the 0th element of vector 2. And then the first element of vector 1 multiplied by the first element of vector 2. So that's Hadamard. You can do dot products. Okay? Each one of these lines is two equivalent ways to do Hadamard multiplication. And here are 4 equivalent ways to do a dot product. Okay? So again, this stuff, you're going to get all the same answers in the 2 ways to do Hadamard and the 4 ways to do dot product. But, as usual, programming languages offer you more than one way to do the same job. So, let's take a look. We can do things like transpose by doing .t. We can, of course, do full matrix multiplication. You've got 2 ways to do matrix multiplication. The operator what's that called? The @ symbol operator is overloaded. And then you can also use the function matmul. Okay, just a bit of notice. When we do things that we will do in this class, we may need to invert matrices. So just a reminder, the matrix inverse is like the reciprocal for a scalar number. So if you take 2 and multiply by 1/2, you get 1, right? If you take a matrix and multiply it by its inverse, you get the I matrix, which is diagonal 1s and 0s everywhere else. Okay. So matrix inverses, well, they're one of a whole class of operations, which when you do them with floating point numbers, they don't produce exact results. They could be off by the smallest possible amount that you can see in a floating point operation. Typically, this is like 10 to the minus 20 something. I don't remember the exact number nowadays. But it's a tiny number that it could be off. Okay? So NumPy gives you, because you can't do equals on something if it could be off by a tiny fraction like 10 to the minus 16, right? So we have NumPy all close, which will tell us if things are close to each other within a tiny 10 to the minus something. So here we take our matrix, we invert it, we ask if the definition of a matrix inverse is that the matrix times its inverse, matrix multiplied by its inverse, should be I. And then we check if indeed it is close to I. Okay, so let me give you a use case. Again, we've seen this use case already. If we have a predictor where we take inputs and we multiply by a set of weights, we get predicted outputs, a y hat. So let's see if we can make a fake machine learning system manually. And the idea is that we're looking for those kinds of MNIST style, really crap images that are just a few pixels, just a few pixels wide, a few pixels high. And the only thing those images can have is zeros or ones. They can either be black or white. So here's an image with a bright vertical line in it against a dark background. Okay? So we're going to need to make these inputs columnar. And you can try a couple of different ways, but the best is to use reshape. So we're just going to turn, and this is totally normal, right, for machine learning systems. We take what had been a two-dimensional image and we reshape it. So we take first the first row, the 0th row, I should say, and then we stack it on top of the next row, which is stacked on top of the row after that. So 0, 1, 0 is that first row, 0, 1, 0 is that second row, 0, 1, 0 is that third row. So by columnarizing it, we make it so that we can do this kind of math. We take our input x, it had been two-dimensional image, and we columnarize it. Okay? Because we know that's the way this is going to work out. Okay. So here I have hand predicted a set of weights. And the set of weights is going to produce a larger y value when there is a single vertical stripe of brightness against a dark background. This kind of an image matrix multiplied by these kinds of weights that I've hand designed are going to produce a large number. And different kinds of images, like if it had bright stripes down the sides and a dark stripe in the middle, they would produce lower numbers in the prediction. So here's an exercise for you. Write the matrix multiplication. Write this using NumPy to make a prediction. And once you've done that, test some other things, right? This is the kind of input that you should produce a big number for, thinking it's a positive class example. These are different kinds of images that you should produce smaller numbers for. They should be negative class. Okay, so I say to you, make a prediction algorithm here using your knowledge of NumPy you've acquired, and use it with these inputs and see if you get the results you expected. Okay, that's it. Talk to you later. Bye.